Hello and welcome to Textbook Engineering Problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition. We're going to be doing problem number 2.34. The problem statement says a chemical reaction going from A to B is carried out in a closed vessel. The following data are taken for the concentration of A in grams per liter as a function of time in minutes from the start of the reaction. Then they give us a chart. It kind of looks like it has a log relationship on the y-axis. Okay, and then they give us a table of values as well. A proposed reaction mechanism predicts that the concentration of A and T should be related by the expression, this expression. Okay, where K is the reaction rate constant. Okay, part A, do the data support this prediction? If so, determine the value of K. Use a semilog plot in your solution of this problem. Okay, so we need to convert this into a linear relationship, and then we can make it look a little more like a line here. So we can say the natural log of Ca minus Cae equals minus Kt plus the natural log of Ca naught minus Cae. So we have something that looks a lot like a line here. So now let's define our equation for a line. Mx plus b. Y in this case equals natural log of Ca minus Cae. X equals T. M equals minus K. B equals ln Ca naught minus Cae. Okay, so that's our equation for the line. Let's move over to the computer and put in our table of values and our function, our model. Okay. So we moved over to the computer here. I've put in the table of values and I've written the function here so we can keep an eye on it. Y and X. So we know Y equals the natural log of Ca minus Ce, which is that value. And we know that X equals T. Okay. Can't really do the last value here because it doesn't really convert when T goes to infinity, and you can't take the natural log of 0, so it's kind of out of bounds for this function. And if you think about it, infinity isn't really a number, and so that's why the model kind of breaks when it's talking about infinity, because you can't actually let a time go to infinity. It's just an expression to say, okay, the reaction's gone as close to completion as we're willing to sit around and wait for it to. It's reached a local equilibrium. Okay, so now we need our parameters m and b. So m equals minus k. We don't know what that really is, so we'll just put that it's 1 for now. We do know what b is. B equals the natural log of the initial concentration minus the final concentration. Okay. And let's program our Y model. Y model equals Y equals m times x plus b. We don't want our m and b to change when I drag this down, so we'll put $signs there. Okay, so it looks like 1 is a pretty bad estimation of what our slope is. So it actually looks like it should be a negative. So maybe we'll do a negative 0.1 or something like that. That's a little closer. Okay, but we'll let the computer figure out the rest of that. Our first guess is initially pretty close. All right, so what we want to do is reduce the error between our model and the data. So let's figure out what the error is. And we want the squared error. So we want the model minus the error, and then we want to square it so that it's all positive. Okay, and then we'll sum all of these data points, and then we'll change m until this is our objective function, until our objective function is at a minimum, and we're going to change our slope. We don't want it to be non-negative. We know that m is negative, in fact, so make sure that's not checked. And then we've reduced our error quite a bit. It's very close to 0 here, and it's given us a slope right here that's pretty close. That should be pretty close to a good estimation of what the reaction rate constant is. Okay, so let's graph this. Okay, it told us that it wanted us to graph on a log plot. So okay, in the problem statement it said use a semi-log plot in your solution of this problem. So we'll put our y-axis on the log plot. So how about we convert our y model over to a concentration, our model concentration. So right here, we'll back calculate what the concentration is from our model. So if y equals the natural log of Ca minus CAE, as we have right here, then we just need to convert these numbers into y by doing a little bit of algebra and putting y in terms of Ca. So I'll go ahead and do the algebra. Y equals ln Ca minus Cae, E equals Ca minus Cae, so Ca equals E y plus Cae. Okay, so now we have Ca in terms of y, and Cae equals exponent of y model plus Cae. Okay. There we go. So we'll chart make a data plot. So X, Y, okay, and then we'll make a model plot, X and Y, okay, and then we will plot this. We'll format the axis to have a logarithmic scale. There we go. So we've got our log plot here of the data, and it looks like our model is just right on top of the data. Let's change our model to be a skinny line instead of markers so that we can actually see the line a little better. Make it a skinny line that's black, and then maybe we'll be able to see how close it is. Okay, so our model fits the data very well. So if we look at part A, it said determine, do the data support this prediction? Yes, the model is very good. If so, determine the value of K. Okay, so we know that K equals the opposite of M. So we found out what M is, so K equals the opposite of M. So there we go. That's our reaction rate constant right there. And that's it for part A. Then we go to B and we say if the tank volume is 30.5 gallons and there is no B in the tank at time equals 0, how much B in grams does the tank contain after 2 hours? Okay, so our time is in minutes, so we need to convert this time. T equals 2 hours, which equals 2 hours, 60 minutes per hour equals 120 minutes. Okay. Volume equals 30.5. There's no B at the beginning, so we just need to run the calculation. We know that we start with a certain concentration of CaE, and then it, over time, goes to a certain Ca concentration. We have our model here, so we can just use our model and find out what does Ca equal when time equals 120 minutes. And that is our model. The concentration is 0.09314. Okay, that's enough significant figures for now. And this is grams per liter of A, or A. The concentration of B is going to be inversely proportional to the concentration of A, because all the A is converting into B. So we started off with an initial concentration of A, and any A that is missing from that initial concentration must be what the concentration of B is. So sorry, my pen's not working super well. So concentration of B equals the concentration and the initial concentration of A minus how much A is still remaining. So anything that's missing from the concentration of A must be what the concentration of B is. Okay, figure out what that equals. So we know that concentration of A naught is 1823 minus concentration of A after that long, 2 hours. And this equals 0.08916 grams per liter. That's the concentration of B. It asked us how much mass of B is in the tank. So they told us the volume of the tank right here, gallons. So we need to convert the volume from gallons to liters. So the volume times the concentration equals the mass. So that equals 30.5 gallons times 0.08916 grams per liter, 3.785 liters per gallon, and therefore there are 10.29 grams of B in the tank after 2 hours. All right, that is it for problem number 2.34. Thanks for joining me. If I made any errors in this problem, let me know in the comments and I will make a correction I'll post a correction in the comments or make a follow-up video. If there are any other problems you're having that you want me to look at with this book, I can take a look at that problem and try and explain things for you in another video. Otherwise, thank you for watching, and I hope to see you in the next one. Thanks. Bye.